happy to be with you. This is what I would like to speak about because I, I actually came here. I had some hesitation, but I came here because when I worked on the origin of plate tectonics more than 50 years ago, I was about your age. I was between 22 and 30 when I did my work, and it was a very exciting time, and we had the impression that something was coming out, but we were not sure what. And it's a time of great excitement, and I wanted to talk to people like you because I feel we are in a situation which is somewhat similar now. I think we are entering from a field of plate tectonic to global tectonic. So I will develop that a little bit. Last June 25 in Paris, we had a meeting for the 50th anniversary of plate tectonic. Actually, we had several the last 3 years, depending on where that was. And in France, this was because I published my paper on the computer model of the motions of plates on June 1968. So we decided that was 50 years. Before that, we had one with Mackenzie because that was the anniversary of his paper. And before that, we had one in 2 years before in Le Mans because that was the anniversary of Pittman's publication of the magnetic profile. So, in other words, it was over a few years that things happened. Anyway, what I tried to give in this Paris meeting, and that's a paper I just wrote for a special issue of tectonics on this subject, is that we were in a situation similar to what the horses that you see here were. I don't know if you know Curzio Malaparte. Have you read Caput? Has anybody here read Caput? Nobody. You are really illiterate, but that's all right. It's a famous Italian writer, and Caput was about his experience during the war. He was on the German side, and he followed the thing. And when he was in winter of 1942, he was in near Leningrad, who was encircled by the Germans. There was a big war. And there is a lake just next to that, which is called Lake Ladoga. And the people had put fire to the forest. And thousands of, or hundreds at least, of horses, afraid of the fire, just went into the lake. But the lake was under freezing temperature, but had not yet frozen. It was super cooled. And when they entered the lake, suddenly, boom, everything froze. And several hundred horses were just being frozen to death. And of course, the spectacle was quite extraordinary. And the question you have is, if the horses could discuss between them, which one would say that he triggered the freezing of the water? That's a very important question, because my feeling is that when we were in these 60s, the earth sciences were in a super cool state. In other words, all the ingredients were there. It was just a question of doing the right step, which was a minor step, and anything could lead to the solidification of the new paradigm anywhere. So that created a very special feeling. Generally, when you write history of science, you try to have a linear thing. This one did that, and this one did that. But this was not like that. It was not what I went through. simultaneously, several people did the same thing, and one was the first to do it. And if he had not done it, somebody else would do. I discussed that in Paris, and people like Dan Mackenzie, Jason Morgan, who were there, and Peter Molnar and so on, they all agreed that that was very close to what they had felt at the time. I take a few examples, but I will not go into that now. If you have questions, I may answer later on. The first one is the obvious thing. The magnetic anomaly interpretation by Vine and Matthews in 1963. Now, simultaneously, Lawrence Morley published the same, tried to publish because he was not accepted, the same thing. He sent the manuscript, and the manuscript was rejected. And he had a different path to think. He used the magnetic anomaly that had been mapped by Scripps on the West Coast, whereas Fred Vine used directly the ideas of Hess, but both gave exactly the same model, simultaneously, not knowing each other, and that was a good indication. You know, anybody could have done it. It was a question of just finding it. This was true also for, there was a long controversy between Jason Morgan and Dan Mackenzie, who first said we have the principle of spherical kinematics, and we can use that to quantify plate motion on the Earth. And that was important, of course, because this was the first time that we had really the establishment of quantification of motion at the surface of the Earth. So that was a big step in earth sciences. But Jason did that in a meeting in June '67, but nobody was interested by what he said. And he sent his preprint to a few people, including myself, and nobody was interested except me, which is interesting too, which means that sometimes the ideas which are true and correct, you know, are too advanced for the state of mind of the people, and they don't realize that they are interesting. When I talked to the people in Lamont, where I was working, they said, let's work on that, and that led to my paper on plate kinematics, you know, and, my 6 plates model. All the people I talked to, that was Talwani, Langseth, Pittman, and so on, said, no, we are not interested. We want to work on the magnetic anomalies. So you are not ready to do the jump, but some people do. And then Dan Mackenzie did that. He said independently, although he was in the same meeting, and then after that he had he was among the people in the institute where the paper Morgan was reviewed, and then they asked for revision, which delayed his paper by some time. So anyway, he had a different approach and published something before Mackenzie, before Morgan, but with the same path of mind, but different way to present it, and both published, I mean, both were conceived at the same time and apparently completely independently. So that is second example. The third example is actually the seafloor spreading idea itself. I was in Lamont in '59. That's when I arrived. I was 22 at the time, and I was sent on the worldwide mission on the mid-ocean ridges. The idea was to test that the earthquake belt that followed the mid-ocean ridges was actually connected to a mid-ocean ridge and to a rift valley. And we had to zigzag on this line of epicenters, and each time we crossed we could see the bottom rising up and so on. We arrived to the crest. There was some kind of valley where the This is the Rift Valley, which is not sure at all, but that was in the south of Africa. And we would send a telegram to Lamont, to the boss, who was Maurice Ewing. We have found the reef where it was supposed to be. See, that was a very exciting time, because for me, that was the first time that you have predictive earth sciences. You know, we had just a line of epicenters, and we discovered the structure that was supposed to go with that. But at this time, in Lamont, Bruce Hazen and Maurice Ewing had just published a few years before the idea that this line of epicenters, which is 60,000 kilometers long, was the largest tectonic structure at the surface of the Earth and was related to extension. And Bruce Hazen had a step further. He as the belt was going into the Rift Valley in Africa, he said the whole thing is extension and production of new ocean crust. So that was already the idea of formation of the ocean crust. And then the following year, a guy from Tasmania, Australia, Carey, just published the idea but adapted it to his expansionist idea of the world. And that was exactly the same idea. And then finally, Hazen got in a seminar, Harry Hess in a seminar in Princeton that was given by Hazen, got the information on the Mid-Ocean Ridge and decided to have seafloor spreading. So for this idea of expansion of the ocean and formation of new crust, the idea came more or less independently to Bruce Hazen and then to Carey in Bruce Hazen in Lamont, Carey in Tasmania, and then shortly after was summarized and presented by Harry Hess. Donc, these are three examples of things that really were more or less simultaneously coming out. So that's the point. Is the state of the research is such that it's normal to move to something new. Well, in this meeting in Paris in June, I got really the feeling that we had entered into a super cool state in geodynamics, and that we might move from plate tectonics to something that will really relate it to mental dynamics. To me, this is probably the beginning of what's happening. One of the things that was very clear was with the presentation by several people, but Barbara Romanovich in particular, on the structure of the mantle, of the lower mantle and the core mantle boundary, was the difference between the lower mantle with the fact that it has limited convection, few vertical plumes, but which are very thick and fat. You know, certainly know about that, 1,000 kilometer wide or so. And then they rise vertically, and then suddenly when you come to 1,000 kilometer depths, everything changes and you enter into something very different, exuberance of multiple and vanishing structures and so on. And then the second point, of course, which is now becoming so clear, the lower mantle is governed by the lower order harmonics, in particular harmonics of 2, and that is related to the axis of inertia of the Earth. So this was something that was coming throughout the meeting, and the relation with Pangea and flood basalt and so on. So the feeling was shared by quite a few people. Peter Molnar had about it, and he's going to write about that. And then, of course, Barbara Romanovich, and then other people like Claude Jopard and so on. So the feeling was, are we on the verge of some major change that we are not yet completely sure of, but which will, for the first time, integrate plate tectonics into real mental dynamics. You know, have a clear relationship. Now, I first started working on that when I published with Philippe Pichon in 1984 a paper on the Pangea. And I just showed a figure of my paper with Philippe Pichon. Now, I'm going to use that quite a lot in this. So you have to get used to this type of geographic projection. This is a Lambert equal area projection. Okay, in other words, anything on this map respects the surface. There are no distortions. There are distortions, of course, but no distortion of surface. And the great advantage, of course, is that the hemisphere, if you center it like that, the hemisphere is a small circle on that, is a circle on that. And then that's the first hemisphere. And then there is an artifact. The second hemisphere is projected outside of the first. So what you have, the outside circle is the hemisphere on the other side, which is projected. And of course, this results in extreme distortion for the circle just outside, which is just a point. You see what I mean? The great interest is that you compare the surfaces that are within one hemisphere with respect to the surfaces which are within the other hemisphere. This is why we adopted this projection. And the idea was Pangea really strictly hemispheric, respected strictly hemispheric? In 1984, we took the best reconstruction of the time. This was very obvious, and you can see it. You know, it's clear that it respects exactly a circle, a hemisphere. Not only that, but these are the rotation pole given by paleomagnetics. It goes through the pole, so it's an hemisphere that goes through the pole. So Pangea was within an hemisphere that went through the pole, okay? And you have the age of the paleomagnetic pole in millions of years at the time here, 160, 180, 200, 280, 350. This Pangea, I will develop that a little bit, was effective between more than 200 million years, roughly 230 million years. During 230 million years, it respected this strange configuration, completely encircled by the land is encircled by that. I will come back to that. It's an important point. One reason also is very interesting is that the surface of the continent at the present time, taking the continent at the 2,000 meter depth, water depth, okay? It's 43% of the surface of the Earth. So you see it covers nearly completely one hemisphere, but leaves about 10% of this, or at least 1/5 of the surface of this hemisphere for the ocean. And I will discuss that because this is very important. I will also discuss a point which is very interesting. Tethys, this ocean that was within Pangea during these 200 million years, was always oriented east-west. In other words, the subduction zone that in general was to the north was such that it was nearly kept close to the equator. And it's obvious that that is also something which is not haphazard. Okay, so that's what we did at this time. We pointed out that this was good up to 125 million years before. And you see that by this time, By the way, what you see around is the subduction zone that we infer were present at the time. So it had already begun to crack all over, but it was still within this hemisphere. Okay? And then, of course, after 125 million years, it's the Big Bang. Everything goes out. Not only Tethys will be closed, but you will have all the continents that really move out nearly to the other hand. You see, it's particular for Australia, Southeast Asia, and Antarctica. And we compare that to the geoid of the time, and this is the geoid with the same projection. And we pointed out that the geoid had this order 2 symmetry, and that the axis of inertia that we computed, and that turns out to be exactly the same axis that is now found for the present geoid, of course, but also for what we will talk very soon about, these two pieces of low shear velocity zone on the core mantle boundary, you know, that produces of order 2. If you use the axis that is given by this order 2 thing for this low velocity shear zone on the core mantle boundary, you get the same axis that you have there, and it's very obvious why. It's because this low velocity zone control apparently the geoid, the shape of the geoid and the general shape, and also obviously are related to the rotation of the Earth. We'll come back to that. But at the time we said there is a correlation, this circle which follows the negative all around, the big negative which is all around this central positive, this circle follows exactly the edge of the continent, and we assume that Pangaea was controlled by the same type of low order thing, so that was controlled by deep mantle convection. And we assumed that that was permanent at the time. But we could not go further because there was no information really on what was happening in the lower mantle. Now, in this meeting, I will just go briefly through that. In this meeting in Paris, I take these slides from the presentation of Barbara Romanovich, who made a presentation on the lower mantle structure. First, she showed that when you look at a depth of 2,800 kilometers, that is on the core mantle boundary, and you look at the shear velocity structure, the different models now essentially converge. These are 6 different models, okay? And they all give this high Pacific low velocity, this Africa low velocity, so these two, always the same. And to me, very important, the blue, which is high velocity on the top. So this band of high velocity, which give, when you take a simply order 2, it gives you this axis, which is in the equatorial plane, and which is the same axis that I obtained from the geoid and that I used at the time with Philippe Pichon. Okay, so now the thing also they were pointing out, which is interesting, is that with such a system of symmetry controlling the maximum axis of inertia of the Earth, if you look at the paleopoles, they tend to cluster along a large circle here, which means that there is of course, with this axis of inertia, you can have change along that, along the axis. So you can have migration of the pole of rotation along this great circle. And that indeed appeared to be the case. That point was made in 2010 in a paper by Dziewonsky et al., where Barbara Armanovich was an author. This paper here. And Dziewonsky, of course, pointed out that this structure was found in the lowermost mantle and then extended somewhat above. You could still find there. And then when you look at the power in the angular degree, you can see that it's completely dominated by this order 2 and 3 in the lowermost mantle. And then to find, again, low order, you have to come all the way to the surface. So there was a clear correlation that existed for shear velocity at 280 kilometer depth, but also when you move all the way to shear attenuation in the transition zone. And finally, they said it's also true for the hotspot distribution and for the geoid. And then the final point that was very much discussed in this meeting was the question of the slabs. You know, Peter Molnar pointed out that we have been fascinated by the phase transition at 400 and 660 kilometers. And we all thought that was a real transition between upper and lower mantle. And the main problem for circulation that would stop at this level rather than deeper. And it was a big shock when Fukao and Obayashi really demonstrated that there was quite a few slabs which would go down to 1,000 kilometers, well below the phase transition zone, and that apparently some of them went through. So that indicated that there was a fairly large change, and I'm sure you are going to discuss that, the fact that some people find now that it is most probable that there is a factor of 10 increase in viscosity at this level, 1,000 kilometers, rather than at the phase boundary limit. And then Barbara showed things that you may have seen in the literature. They are quite spectacular, you know. They have made great progress in imaging the change of the S-wave velocity with depth. And you can see here, typically these things rising from the core mantle boundary are quite wide, much wider than expected for a plume, 1,000 kilometers typically, between 800 and 1,000 kilometers. Second, they rise vertically. They seem to be not affected by any lateral motion in the lower mantle. Third, when you pass this 1,000 kilometer limit, everything breaks loose and you enter into something different, which is quite complex. Sometimes you can trace something. Sometimes it's quite distant. For example, if you want to relate the Canary hotspot to this, you see, you have to move more than 3,000 kilometers and the connection is not obvious at all. In other words, once you pass this limit, you enter into a different domain where there is a lot of motion, lateral motion and so on. And finally at the surface, but you will see that better. In the Pacific superswell, note that the best images they have are always under the oceans. They have very few plumes that they can follow clearly under a continent. Actually, there is only one, which is Afar. All the others is very difficult. Note that this here, for example, Pitcairn is especially spectacular and goes all the way to the surface, but others are much more complex and very often what you have is when it comes into the asthenosphere, you have the impression that the material of the plume has been dispersed and occupies a large space. Okay? So, the most spectacular is this recent publication by Nelson and Gren. I don't know if you have seen that in 2018. Here he has made a great progress. This was what French and Romanovitz had obtained for the same place. You see, and here is Nelson and Gren. And what they had, you see, is this is the Yellowstone hotspot, supposed hotspot. And not first the very strange system that if this is the route, you see, you are offset by more than 3,000 kilometers. Second, the enormous amount of low velocity material which is extended all over the asthenosphere for very long distances, and the not too obvious relationship between this and this. Okay, let's move. What French and Romanovitch had shown in 2015. Here I'm still using the slides of Barbara because she's in the heart of this work, and I thought that was good to show what she showed us in June. It's public. You can find it on the all these talks are available on the Collège de France thing of Romanovitch, and you can get them including the PDF of the illustration. This is how I got the PDF of the illustration. And what she shows is this 2,800 kilometer distribution of shear wave velocity. In red, the what they call large low velocity shear zone. And the African, which is not so much on Africa. As you see, Africa is here. It goes all the way mostly into the South Atlantic. And then she says, these are what he calls primary plumes. Now, what she calls primary plumes are plumes where she feels confident that they are directly related to a plume at the core mantle boundary. Okay? There are 12 of these. 12 in black. You can see them, they are in black. Notice that they are mostly in the Pacific, under the Pacific. And then there is, here in the Atlantic, Iceland, and then 2 in the Atlantic. And then there is Afar, the only one under a continent. Then there are others, she thinks clearly resolved, and others somewhat resolved. You have to be careful that in this field, quite a few people are skeptical and say that what she calls somewhat resolved or clearly resolved is not clear at all. But that's the position of, for example, Dan Mackenzie or Peter Molnar. But still, there was agreement that there is a clear relationship between hotspot focused mostly under the ocean, but originating within this low velocity shear zone that have to be of higher density to explain the relationship with the axis of inertia of the Earth. Okay? See, so that's what we got from this meeting. So the conclusion of Barbara at this meeting, I just translated them. Mantle plume do exist. The major upfelling flow is in the form of about 25 broad low shear velocity plume that are located over the large low shear velocity provinces at the surface of the core. The hoods are hot, partial melt, but they are chemically dense. You have to use a different material to explain that they are low velocity and still high density. So there is a big argument going on, and this is not solved at the present time. Second, they extend quasi-vertically from the core mantle boundary to 1,000 kilometer depth, indicating very sluggish circulation in the lower mantle. And third, they are horizontally deflected at 1,000 kilometer depth, indicating more vigorous circulation above. Then, what I conclude of that, which are, call it my inferences. What I'm most impressed by, circumpolar band of high velocities that is present on the core mantle boundary and follows exactly a hemispheric circle, okay? And around the two low velocity and high density things. Donc, this band of high velocity, people have made computation, you know, using simple model. You get slab model going back to 110 millions of years. You assume they go down vertically, and you assume then they finally go to the core, and with that they compute the mass anomaly, and they find a good relationship between the predicted mass anomaly and what they have. So this relates to circumpangea subduction. It's very obvious because that's the only thing that would go to that. The second thing, the complex path of plume in upper mantle and their accumulation within the asthenosphere suggests that they accumulated below Pangea and produce huge flush basalt as breakup occurred. That I am going to develop, but the main thing is that when they come under a thick lithosphere, I will give you argument for that. The flood, the plume material extends laterally, and this is shown by many models, beginning with White and Mackenzie and so on, and extends and doesn't go through. So it goes over a very large width, several thousand kilometers. Donc this material is there and can come, and that has been discussed also by White and Mackenzie, only when you have, with a thick lithosphere, you have breakup of the lithosphere. Then the material coming up begins to melt in great amount, and you have flood basalt that is triggered and extend. But in this case, the relationship with the plume origin is tenuous, and I think really doesn't exist. You are off, you know. The thing that you get on top is it's pure guess about what you say. This is because you accumulate material, it's a reservoir, and you break someplace and it goes up. And I will show you what happens in Pangea. And then the third thing, we should not expect then obvious direct relationship between flood basalt and lower mantle plume exact locations. Okay, that's my inferences. Now, what we have done is very simple, and this I did with two colleagues from Turkey, Caner Imren, who did all this nice illustration that you will see, and Celal Şengör, which discussed the tectonique. The first thing was checking that if I take the latest best, supposed best, reconstruction of Pangea today, do I still get this remarkable hemispheric configuration? So I took Müller et al. 2016. It's very easy to use. You know, they have everything on their site. You can get all these things easily, and they give all the details. You can even manipulate the thing and so on. And here is 220 million years. Well, I don't know why, but this gives an ellipsoidal thing. On my computer, it's purely circular, but it's a question of projection, I guess. Anyway, you have to believe me, it's purely circular. For some reason, it's completely changed there. What you have in gray is continental masses. Okay? You can see the continental masses, a little bit off here, little bit in here. Here you have Tethys. here, and then you get there. So remarkable, uh, remarkable hemispheric configuration for 220 million years. That is the end of Permian time and entering into Triassic. Here you have the two geographic poles that they give based on their reconstruction of paleomagnetics. Now, what we did is to take their reconstruction, put it in this projection, and then find the best projection by shifting, because we have the problem of absolute position. You know, they have, and this is a very difficult question that I will discuss briefly. We know nowadays how the pieces are with respect to each other. But as you move back, as you know, paleomagnetically, you lose the longitude control, right? So you have to use something else. Some people use no net rotation. Some people try to use hotspot, and that leads them to catastrophes, I think. And then some people try to use subduction zone by model with the slab going down, and that forces and so on. So there are several things. I will show that. I think demonstrate that no net rotation, the NNR model, is the one that really fits the data. And it creates some very strange thing. For example, in complete disagreement with the paper my friend Laurent Husson published a few years ago in South America. Well, but this is controversy again. Huh? I'm not trying to say this is proven. I'm saying we are entering in a field where this makes sense now, and we should look at it very carefully. So this we did for, just to compare, I used also other reconstruction. This is Cotesi, 2017. It's the same thing, but here but it's exactly the same. It follows exactly the same small circle, but it has the advantage to show you again the Neothetis and Paleothetis. There were two different oceans. And notice each time, that's a very important point, the subduction zone in Tethys are to the north, and they are maintained roughly along the equator. And you know, if you think of subduction zone as producing slab, which are high density anomaly, the fact that they align themselves in the equatorial plane along the plane where defined by the maximum axis of inertia is, to me, very important. Actually, I argue that this subduction zone prevented Pangea from rotating widely in both directions. It meant each time it brought it back to the proper direction. We did not do the reconstruction all the way to 340 million years. Why? Because they become less and less sure as you get back. But essentially, starting about 340, 50 million years, you are dealing with a hemispheric continent, with a Pangea, which is again along the equatorial plane. And this has been going on for at least 230, well, not at least, about 230 million years. It began a little bit before. You have a difference, which is you know that this have been called this Gondwana and Laurasia. Gondwana is the system of continent to the south, which included South America, Africa, Antarctica, India, Australia, etc. And then Laurasia is the continent to the north. Notice that the characteristic of Laurasia is that it will be fabricated progressively by accumulation of pieces throughout the period going from 350 to 250. And there has been all these pieces will will get together and progressively converge and form something more complex. Okay? Then let's just look at the thing as they move every 20 million years. Again, these are reconstruction from Muller et al. We did not touch them. It's exactly as they gave it, including the poles and so on. And what you find is very clear. You respect this. I'm shocked by the fact that it gives ellipses here. There is a problem with les ouches, you know. Something is wrong. It's purely circular. When I make it on my projection at home, it's purely circular. It's some trick of physicists here. I've always been a very little bit careful with physicists. Well, anyway, this indicate, as you see, 220, 200, 180, 160, no change. Yes, there is a change, but no change in the hemispheric structure. The continents are completely contained within one hemisphere, which goes through the geographic poles. Okay? But there is a difference. You can see that this red thing indicates that this is the Proto-Atlantic Ocean, this is the Proto-Indian Ocean. It begins to break. And then you see this Paleothetis disappears. Okay? So this Neothetis increases in size at the expense of Paleothetis and at the expense of the production of new breakup within the continent. And this is done through overall increasing clockwise rotation of the continent. Okay, Pangea has a clockwise rotation, which eats Paleothetis, the blue thing over there, you see, and at the same time opens the breakup behind. So, but it's within the continent, within this Pangea hemispheric continent. All the way to 160, it doesn't change. I go to the next sequence, and the big major change happens at 100 million years. But let's just first consider at 140 million years, something important will happen. The continents begin to move out. You see that from 140 to 120, you see, for example, the North American continent moves out by more than up to 1,000 kilometers or so. Same thing for Northeast Asia, moves out. Here, no. One remarkable thing is that when you keep it this way, you find that South America stay close to the border and doesn't move. It stays close to the small circle everywhere. Very little motion. This is also what NNR gives you at the present day. Very little motion for South America. Whereas Africa, which is, it's interesting. There are several interesting papers by Burke, if you look at the thing, and colleagues. And he argues that the thing that was at the beginning of plate kinematics, which is that Africa being surrounded by ocean ridges that moving away, obviously it should not move, you know. But this is a very strange concept when you think of the whole thing. Actually, when you look at Africa, it has moved to the northeast all this time, and this is now very clear. So, to 130 million years, continents begin really to move out. Now, you can discuss about the cause. Of course, we know two things. One is the fact that many people have discussed since 40 years. The first to mention it was Don Anderson, that if you have the larger the size of the continent, if it stays over a piece of asthenosphere for a long time, you will heat up because the continent doesn't evacuate enough heat. And most of the people show that for a Pangea-sized continent, it's at least 100 degrees in 100 million years. This is more than 200 million years. Of course, you have to take into account the fact that the presence of Tethys actually diminishes the system by a factor of 2. And that's why Tethys is so important for the heating. And the second thing we'll see for the hotspot too, the accumulation of hotspot. If you have a lot of plume material coming all the time, as we know that we do, and it accumulates and there is no break, well, you have more and more magma below, and obviously something is going to happen. Anyway, these two questions lead to something which is probably the cause of the major disruption of Pangea, starting 130 million years, with continents moving out, and finally, 100 million years ago, everything reorganized, and at the same time, Tethys is being closed in a scissor-like fashion. This is opening like that. The pole is there, and it just closed like that, with India and so on. So you have both this closing here and the continents moving out. And this you see very clearly in the last stage, 60 million years. See, by this time, India has nearly come there, and by 40 million years, it's finished. In India, the Tethys is closed. Okay, you have closed the Tethys. Now, the only possibility of motion, of moving continents, is moving the continents out. And that's what happened, and it becomes very, very important for the system Australia-Antarctica that will be moved laterally and pushed out a very large distance. Now, if you look at the present-day geoid, I showed you a geoid 30 years ago. I just took EGM 2008. It's supposed to be, specialists told me, the best at the present time. Anyway, you see that the hemisphere that we had computed with Pichon has not changed. It's the same within 5 degrees, the same thing. So the axis is the same about here. And you have this, the blue are the negative anomaly. You have this negative anomaly going all the way, which is quite wide. You see that. And you see that the negative anomaly really comes within the Eurasian continent here, whereas it is along the South American thing here. And this is because, I will discuss that, Eurasia has moved out in this direction. So essentially the geoid, and it's not surprising, show the same low order structure and so on. I just show you the other side. This is centered on the Pacific now, so that you can realize what's really happening. You see the broad negative belt. This is Australia, Antarctica, South America, North America, Eurasia. So it enables you to see the same thing. What is very spectacular is this broad negative that you have here. Now, looking at a geographic map with the relief in the ocean, that's the present ocean. It's very interesting that you see here the 90 East Ridge. Now, the 90 East Ridge is supposed to have been produced by a hotspot, and it's a volcanic ridge which has been produced between 40 and 120 million years. You see the trace here very clearly. This is the hemisphere, by the way, the circle based on the geoid. And then you see the Chagos-Lacadive, which respect the same kind of curvature. And actually what they do, both of them, is respect the kinematics of closing of Tethys. And what it tells you is simply that India has followed this closing of Tethys and had left a trace there. And when you move back India with 90s, and there you find that it doesn't respect at all a system that will be related to an independent reference frame. This is just the bathymetry in this system. And the reason I show you that is because it shows you both the fact that north of this limit, which separates South America, Africa, and go all the way to here, the system is related to the closing of Tethys. And you see this small circle thing that are related to the closing of Tethys, which is Chagos, Lacadive, 90 ridge. South of it, it's completely different. You see here by the structure and the magnetic anomaly show you the same thing. These two continents, Antarctica and Australia, separated away, and this limit was there. So the limit here, this system is the one that moved the continents out, and then this whole Southeast Asia moved out also in this direction. Now, if you look the same thing but centered on the Pacific to better understand what happened, what you have done is very clear now. The continents have moved into this hemisphere in a spectacular fashion, in particular, of course, for Southeast Asia, Australia, and Antarctica. South America has kept at the limit. Northeast Asia has moved a little bit, and North America more. So what you have is a rectangular, more or less rectangular, if you can speak of rectangular on the surface of the Earth, but a system in which you have essentially an opening like that, you know, between the two, where this has moved somewhat with respect to the reference frame, where this has kept without motion. And it's interesting that if you look at the NNR model of Argus eta, I just took NNR from Argus, the blue vectors are the actual no net rotation model of Argus et al. And you see that South America has very little motion, that Africa has a fairly important northeast motion, that Northeast Asia has a motion like that, and that the main system has been producing, and that has been known for a long time, a lot of slab along this Northeast Asia side and along the South America side, in both cases. So what you have is really something at the present time which resembles the motion that is predicted by simply arguing that the reference frame that is given by this geoid and by Pangea actually is identical. In other words, that the reference frame of the mass anomalies along the core boundary has not moved. You know, that's a big question that is being discussed. Has not moved and has controlled the situation. So let me just summarize some of my important conclusion, important for me, I mean. That's the one that are important in the paper I'm presenting with Channer Imren and Jelal Shangor. First, Pangea was fully hemispheric during 220 million years. This is a fact, and that's something that you have to explain. It cannot be just a coincidence. You don't have a coincidence working for 220 million years. That's not true. There is a system of forces that maintains a hemispheric configuration for Pangea during very, very long geologic time. And this system of reference is the same that the one that we have at the present time at the core mantle boundary. That's my first conclusion. The second, Pangea is tied, and that comes from the preceding, the fixed lower mantle reference frame. Motion closest to NNR. When I compare to all the motion, the other one which should be closed, note, and that's interesting, is the one that uses slab anomaly as a reference model. This one is close to NNR. And the people who discuss the absolute frame of reference all mention that. But they say we cannot accept that because we have to take care of hotspot, which to me is something in which they went completely wrong. That disagrees with other models, including hotspot. So that's a very important point, and I think it means, and I think this is obvious if simply you think about the way this has been going on, that what we call hotspot at the surface is not necessarily connected to absolute motion reference frame as defined from the mantle. There has been so much distance sometime, even now, between the supposed route and the system. And second, it fills so much asthenosphere with plume material that I don't see why it should be each time at the same place. And third, it fits the kinematics of closing of Tethys. For Rio Grande and Walvis Ridge, it fits the kinematics of opening of South Atlantic, etc. So that means hotspot was a very beautiful idea of my friend Jason Morgan. He had extraordinary intuition when he showed us. I remember still the seminar where the first time he presented at Lamont the hotspot model, and he started saying, let us assume that there are 12 plumes coming from the core mantle boundary and going all the way to the surface. And I raised my hand and I said, but Jason, why do you assume that? We don't want to assume that. What is the cause? What is the reason? He said, let us assume and see the consequences. Well, that was a prodigious intuition. He works like that, Jason. But it led a lot of people to make, I think, wrong inferences because they applied systematically the model and concluded that any kind of plume-like at the surface, result at the surface of the Earth, it will be necessarily connected to this reference frame at the core mantle boundary. Second thing, this, if we accept this reference system, it predicts stationary South America trench system. And on the contrary, east-southeast moving Northeast Asia trench system. Now that's very interesting because what is the difference now between these two systems? Do you know what is the difference between South American trench system and this system which is opposite Northeast Asia? Japan and all that, Philippine Sea and so on. What is the difference between the two? Yeah, what do you have of Asia? Lot of marginal basin, right? Philippine Sea basin, Japan Sea basin, and so on. Do you have any of South America? No. The stationary trench did not produce marginal basin. The steady motion of Northeast Asia produced a large amount of marginal basin. And I think that is very important. It is the same thing that I found out in Aegea. In Aegea, you have Aegea is moving southward. The Crete and all that. We are in the Mediterranean now, for those who are so physicists that they don't know what Aegea is. So you have Turkey and Greece that moving to the south, and the system is such that as they move south, they have extension behind, which is produced, and on a much larger scale, this is what happened to the northeastern Asia. So the system is, when it's stationary, no marginal basin. When it's moving toward, it produces marginal basin. That's what I get from the data. That's all. Then, last thing is very interesting too. Very long subduction produce a specific 2,000–3,000 kilometer wide tectonic belt that, in a very interesting paper that very few people mention, Mackenzie et al. In 2015 proposed to call Pangaeite. The southern part corresponds to the Samfro geosyncline of Dutroit. Let me just show you the thing. First, I wanted to mention that it started, but first point started 340 million years ago. I already discussed that, and went all the way to 130 million years. Pangaea was 230 million years. Second, the continents moved within the Pacific hemisphere, but not in a symmetric fashion. South America was stationary, Northeast Asia moved on and produced, and most of the subduction was along here and along here, very little here compared. Then, this is the paper by Mackenzie. It's very interesting. You know, he's a good friend, and I have had many arguments with him. But I remember once I told him, Dan, in your latest paper, one of the equation has a mistake, and it's not right. You should, it's a misprint, you should correct. He told me, Xavier, I never correct my mistakes in the paper because they are voluntary. I said, why? He said, because I hate these people who take my formula and apply them without verifying anything and just do it without understanding a word. So I systematically do things like that. Well, in this paper, he does something similar. It's very typical of Dan, this kind of thing. He makes a reconstruction of Pangaea. Now, he used a completely different system, an oblique Mercator. Anybody here knows what is an oblique Mercator? I know it's mathematics, not physics, but still you use mathematics. Anyway, it's Mercator, you know, it's you have an axis of projection that goes along the pole that you choose, right? And then oblique Mercator, you move it from the pole to have the best option for you, right? And he gives the pole of projection, but he says, I don't give the longitude because anyway the longitudes are arbitrary. But actually he uses a reconstruction that he did himself using some finite motion of his paper with Clayton on the Indian Ocean 40 years ago and so on, mixing the whole thing, a strange bag, and in such a way that nobody can really check what he did. And that's also typical of him. But anyway, what is very interesting is that you recognize Pangaea like that. Red is the ocean, you know, the circular shape. And now it's Mercator. The southern geographic pole is there at the time. The northern pole is there. You can recognize, I think, South America here. You see, South America. North America. You see Australia and so on. Maybe I can get in India. India, you see here. Okay. What he does is very simple. He uses S waves to predict the thickness of the lithosphere, because he claimed that S waves can predict a given temperature. So on this basis, he says I can detect lithosphere by S wave, which is thicker than 150 kilometers. And these are he takes them on the present Earth. Now, second step, he projected this. It has not changed significantly since Pangea time. And I project this thickness of lithosphere in Pangean time. Okay? Now, what you have here is the lithospheric thickness. Blue is very thick. Red is not so thick, 110 here, 260 here. And then, so essentially, this Tethys part here is thin lithosphere. And the whole belt outside, which comprises South America and North America, is thin lithosphere. And he says it's thin lithosphere because it has been affected by subduction during the whole Pangea time, and it has been weakened and is much less thick. Okay, less than 110. That's an interesting point, because indeed, imagine Pangea during these 230 million years with this Pangea subduction acting all the time. Of course, it should affect the system over a width of about 2,000–3,000 kilometers, which is exactly what you have here. Second thing, you see that the core of Pangea is made by very thick lithosphere, more than 150 and often 200. The pieces now fit very well. I'm always a little bit careful with Dan because he tends to arrange things a little bit. But basically, it seems all right. You know, it's a core of very thick lithosphere. And then finally, you enter into a system that he doesn't understand too well. He's not sure why here he gets thin lithosphere again. And I think it's simply because you enter into Tethys and the closeness of the subduction zone of Tethys. But the main thing is you have a core of very strong material that occupies the whole outside of Tethys, okay? With two zones limit between. So, I come now to Pangean flood basalt, what I have to say about that. Flood basalt affect only, and that's very important, only the 3,000 to 4,000 kilometer wide thick craton-like lithosphere. In other words, the part where he has very thick lithosphere. You have no flood basalt outside of that. Between the thin Pangeaites and the Tethys provinces. In other words, the whole flood basalt system is within this very thick, mechanically strong lithosphere. That's an interesting point. Huh? Second, the flood basalt migrate through time in a systematic direction from north to south, from 250 million years in Siberia to 60 million years in Deccan. Third, if you look at each place, what do you find? You find first there is 20 to 10 million years fracturation, a phase of fracturation. You see that, for example, in for what is called the Camp province, which is the whole Atlantic opening, what will become the Atlantic opening province. Now this Pangea, this Camp system, it begins to fracture 220 million years ago in Carnian-Dorian time. And you have fracturation, you have volcanism coming, but a different type from the flood basalt volcanism. And then immediately before the opening of the Atlantic at 201 million years, enormous flood basalt that covers 10 million square kilometers. Enormous. Why is that? It's clear that it is related to the opening. You find that again for the Karoo system, you find that for many other systems. So, let me just show you that. Here I did that myself, so it's very, very poor, but still you will see a better one just after. In red, you have the flood basalt provinces. It's difficult to estimate exactly. It depends of the people. Each time I took the largest possible one that they give. Okay, this is the camp, this enormous thing that covers the east of North America, Africa, and northern Brazil. 10 million square kilometers. This is the province in Siberia. This is 250 million years. This is 201 million years. Then you have the system between South America and Africa, 132 million years. Each time it's immediately after the, before the opening. Then you have the system, the Karoo system here, 183, because this is the proto-opening of the African, proto-Indian Ocean opening. And then finally, here you have the system of Deccan and the system of Kerguelen, 60, 90, 120. So you see the progression like that. And this progression, each time you wait until the breakup occurs, and immediately, boom, enormous flood basalt that goes. Okay, I show you the reconstruction that my friend Channer made. It's supposed to be much more exact. This is Pangea at 220 million years, and on top of that, the reds are the flood basalt provinces. Here, Siberia, 250. Here, Camp, the whole North America, East North America, Africa, Brazil. Then South America and Africa. Here it's between Antarctica and Africa. And finally, this is related to the breakup of India. So this system, each time, the flood basalt appears about 20 to 10 million years after the beginning of fracturation and of light volcanism, followed by the typical flood basalt thing. Okay, I come back to that. Donc that to tell about the 2010 million years fracturation. The flood basalt appear during the breakup. It may lead to continuous volcanic tracks after, as hotspot, interpreted as hotspot, but that trace relative kinematics of opening. This is 90 East region Chagos. And it indicates that magma accumulated below lithosphere and was released by breakup. This is my interpretation. Below the thick lithosphere that the hotspot cannot break, you accumulate huge amount of plume material, and whenever a break occurs, whoop, everything goes out, and you get the flood basalt. And as a consequence, what you get on the surface after on the continent doesn't give you indication on some supposed reference frame in the mantle. Okay? Okay. I already discussed that, so I move that. Then the last thing, Pangea and Tethys. That's a very important and interesting point too. I told you already the total surface of continent above 2 kilometer depth cover 40.6% of the surface of the Earth. Average altitude 453 meters if you use a simple model. The first question I ask, is this near agreement between half surface of Earth and surface of continent a coincidence? Or is it the result of dynamics? In other words, dynamics has confined during a long part of the history of the Earth the continents to be contained within one hemisphere. Question, I have no answer for that, but this is the question I have. Second thing, Tethys surface about 20% of Pangea hemisphere. Role of ventilation of heat, but also evacuation of flume material. It has two ways to act. One is because you have ridge formation and subduction within the Tethys system. So you vent a lot of heat, right? But also you vent and evacuate the plume material that is coming from the side of Pangea, and so that all the system of the Tethys is without any flood basalt. The flood basalt has been eliminated. Third, I believe that the fact that east-west, the subduction of Tethys is essentially east-west all the time during the 230 million years, is because it maximizes moment of inertia along equatorial plane. Thus, any migration from the equator leads to circular motion of Pangea to adjust. It just has to shift, and because it's along an axis of inertia, you see, you can move it any way you want. This is done by transfer of pieces from Gondwana to Laurasia with clockwise overall motion before 140 million years. Finally, scissor-like closing of Tethys occurs between 150 million years as massive outward motion of continent also occurs. Today, nearly half of the continent have moved out of the hemisphere. Well, I'm not going to discuss that more. I think you maybe I could enter into details. And I will finish with that. Back to Tethys. This is another paper that has been accepted for the Canadian Journal of Earth Sciences, where we have a new approach to the opening of the Mediterranean Sea. The reason I bring it here is because it tells us something, because this occurs at the same time as the North Atlantic breakup and the formation of this big flood basalt. Now, what we did is fairly simple. We look at the Eastern Mediterranean. This is the Eastern Mediterranean, by the way. Turkey, Greece, North Africa, this is Libya, Italy over there, okay? And then what we have are the active fault in upper Jurassic, which are well known from oil people here, and which correspond to the time where this basin, this is very well known by oil drilling and so on, was opening. So this opened at the time, and you can follow this. It's along the general direction of the present-day subduction zone below Calabria. And of course, this was previously an ocean. So there was an ocean like that, which is now being subducted in the same general direction. Now, if you look at gravity, free air anomaly gravity map, you see what we interpret as major transform fault. And what we think is that there are three, we document that. And we propose that the Eastern Mediterranean was opened as a pull apart, like that, okay? Again, I cannot discuss that. It will be too much for you. And we'll have to enter into geological detail and so on. But so this is the way it was in Triassic time. It extended all the way to here. And it's, what's remarkable, it's perfect geometry. Perfect kinematic geometry, like you predict, you know, in simple, rigid kinematics. So basically what you had when you open the Atlantic, you begin to move that away, and you had one big transform foil like that, and out of that another one here that opened the Eastern Tethys, the Eastern Mediterranean, sorry. This I compare to a remarkable object that you may not know, but we are now in the Caribbean. and that is the Cayman trough. Now notice the scale. This is 250 kilometers, and the trough is present all the way here from South America, north of Haiti and so on. Cuba is here, Hispaniola here. Okay, so what you see below is the magnetic anomalies, and you see how it opened like that, and you have this system, which is really a pull apart, in which you create something which started 50 million years ago, still active today, and putting oceanic crust in between. We think it's the same type of opening that occurred in Eastern Mediterranean. Now the question I have is, why was there this remarkable small circle thing both in the Caribbean and in, yeah, finished, and there. And that, I think, is related to the state of the lithosphere there that has been transformed, in this case by a major flood basalt in 90 million years ago, for the other one, the Camp event. So, all you show there is that when you look at motion of Africa with respect to Eurasia, the motion, and from 180 to 100 million years, it pure strike slip, and then you have the scissor-like shortening that occurs starting at 100 million years and after. By this time, you are all very tired, so that comes to my conclusion. A few thoughts to conclude. I believe we enter into a new era of geodynamics, but we are still far from a global comprehension. 2, the question of the absolute frame of reference is crucial, and I believe that it has misled many of us. I think that Dziewunsky et al. 2010 were correct when they assumed that, and I quote, the large-scale heterogeneity at the base of the mantle, from early in the history of the convecting mantle, remained locked in place with respect to the Earth's rotation axis ever since, and is currently imposing the planned form of flow in the mantle and of plate tectonics at the surface. Third, I believe that NNR is at present the best reference frame and is the easiest to relate to this absolute frame of reference, which tell us a lot about dynamics. Second, we should be very careful when using hotspot for absolute reference frame, especially under thick continental lithosphere. It's very striking that of the 12 sure hotspots that Barbara Romanovics connect from the surface to the core mantle boundary, 11 are below oceans. Second, we should be very careful when evaluating the dynamics of a given area independently of the global context. In other words, the global context imposes conditions that are not just marginal, but change the whole system. Third, we should consider seriously the possibility that Pangea-type tectonics were governed by quite different modalities than present-day tectonic. This is like what I tried to explain a little bit, but I did not have enough time, and I'm sure you did not understand much of what I said. And then 4, I am talking here about the last 350 million years. Of course, the Earth is 4,500,000,000 years. I let you decide how careful we should be when dealing with much older history. Thank you. No, I'm talking about science. In other words, I think that geology, geophysics, everything will be integrated. In other words, when we do